For his dumbfounding contributions to the field of material science, Kaku has truly noted that the James Webb Space Telescope has discovered 6 immense universes that specialists once believed were incapable of existing. These evaluations have the potential to open up new perspectives on how we interpret the universe. The simplicity of the discoveries is both captivating and challenging to existing theories about the arrangement and evolution of galaxies. It is vital to focus on these revelations, and the assertion by such a respected expert emphasizes the significance of these disclosures. Kaku is an exceptional figure in the scientific field. A physicist of American and Japanese heritage, he is regarded as an expert in both classical material science and quantum mechanics. Unlike some more conservative and cautious thinkers, Kaku has been open to the astonishing possibilities presented by the James Webb Space Telescope mission. His eagerness to embrace new discoveries and share them with the public reflects his commitment to advancing our understanding of the universe. We are grateful that this renowned expert has chosen to break his silence and openly share what can no longer be denied. The strong and clear tone of this extraordinary physicist is evident in his comments on the discoveries made by the James Webb Space Telescope, reigniting his interest in the field. Join us as we explore the implications of Kaku's openness regarding these 6 colossal galaxies. Kaku has consistently been able to contemplate new theories. Throughout his life, he has demonstrated openness to ideas that challenge conventional thinking. Acknowledging Einstein's theories of relativity and Newton's laws as fundamental but limited in fully grasping the universe's intricate design, Kaku believes that the discoveries from the new telescope could drive progress in cosmology. However, many of his colleagues still struggle to accept this view, which has caused concern and skepticism among Big Bang researchers and critics of quantum mechanics. For Kaku, however, this skepticism is simply amusing. The James Webb Space Telescope has revealed 6 massive galaxies dating back to the universe's earliest epochs. Each of these colossal systems contains more stars than our own Milky Way, despite having formed just 200 to 700 million years after the Big Bang. The team of astronomers who made the discovery has named these remarkable galaxies universe breakers. If confirmed, these findings would radically transform how we view the universe. The impact of these revelations is profound, suggesting that the universe's early years were far more dynamic and complex than previously thought. The prevailing theory of how the universe began tells us it was chaotic after the Big Bang. The first solid objects took a long time to form, and it took much longer for them to reach the critical density needed to produce light. The development of complex structures, such as galaxies, was thought to have occurred much later. Yet some of the recently discovered massive galaxies surpass the size of the Milky Way, and their intense brightness suggests they were likely forming numerous new stars each year. In contrast, our own galaxy forms stars much more sporadically. It remains unclear exactly when the first structures formed, and scientists have yet to reach a conclusion. One thing is clear. At the beginning, there may have only been individual stars or small clusters of stars that eventually merged into larger structures. Over time, smaller galaxies supported the formation of more massive systems. Previously, it was believed that such large and complex systems could not have existed at that time, raising the question of whether the universe is much older than previously thought or whether these giant galaxies formed much earlier than expected. This situation is difficult to reconcile with conventional science, which still faces challenges with this model. Some branches of material science have outright dismissed these discoveries and questioned the accuracy of the age estimates. Kaku is aware of this and remarked that many outdated models and theories continue to persist due to the influence of well-established experts. Many of these theories were scientifically disproven when key research revealed their flaws. The truth in any science, particularly in material science, lies in the work of experimentalists who keep theories sharp and accurate. Kaku further explained that here on Earth, we have very limited knowledge about the true origins of the universe. This statement underscores the importance of consistent testing, updating, and reaffirming in the scientific process. The theory of how things began was first proposed in 1927 based on observations of the universe's expansion. This data led to the conclusion that the universe began from a single, infinitely dense point and has been expanding ever since. At the time, it was difficult for people and scientists to comprehend a universe with both a beginning and an end. The concept of an eternal universe was beyond human understanding. Even today, scientists struggle to fully grasp it. Nevertheless, it is essential to consider these possibilities, even if the new discoveries do not align with long-accepted theories about the universe's origins. Science has repeatedly shown that reassessment and openness to bold ideas are crucial to the scientific process. For instance, when Einstein was young, it was once believed that stars and planets were fixed in the universe and that their specific arrangements occupied defined spaces. However, we now know that everything in the universe is in motion. Planets orbit stars, stars move within their systems at speeds of several kilometers per second, and entire galaxies travel rapidly through the universe, whose ultimate fate remains uncertain. This astonishing understanding of the universe challenges long-held beliefs and highlights the need for continuous inquiry and evolution in scientific thinking. Today, scientists are tasked with identifying anomalies and establishing that theories remain inadequate until fully tested or confirmed by observational data. The idea of the Big Bang arose from the observation that galaxies are moving away from each other, with their distance proportional to their separation from Earth. This hypothesis, known as Hubble's law, suggested that the universe has been expanding over time. Factors such as cosmic microwave background radiation, the redshift of light from distant galaxies, and other cosmic structures seem to support this hypothesis. However, it is important to remember that people once believed the Earth was flat and that the Sun revolved around it, even when they had observational evidence supporting their beliefs. Only new discoveries or technological advancements provided a clearer picture. At this moment, we find ourselves in a similar situation. Researchers anticipated that the new James Webb Space Telescope would confirm questions related to the Big Bang theory. Instead, it has revealed 6 massive galaxies that seemed impossible, challenging current models. This demonstrates that science is always evolving, and experts must remain open to new discoveries and re-evaluate existing theories based on available evidence. The astounding discoveries have challenged current understanding and prompted a reassessment of long-standing cosmological theories. Researchers use redshift as a tool to measure various parameters in the study of the universe. Redshift, otherwise called the Doppler impact, alludes to the change in the shade of light as light sources and spectators move relative to each other. To comprehend this, envision hearing a vehicle approaching you. Its engine gets louder. However, once the vehicle passes, the sound decreases. This occurs because the sound waves change as the vehicle moves. A similar principle applies to light. When a light source, like a far-off star, approaches us, the light shifts to blue tones. Conversely, when the light source moves away, the light shifts to redder tones. This phenomenon is called redshift. Physicists have converted redshift values into rates and distances for evaluation in the study of the universe. However, it is vital to note that even a small error in these calculations can have significant consequences. Past evaluation methods are currently under review. Recent discoveries related to our universe require careful consideration of whether they are truly based on redshift errors or if some researchers are simply dismissing facts. This is a question that demands careful assessment and a thorough review of the data and methods used in the analysis. Continuous assessment and reassessment of measurement techniques highlight the growing understanding of ongoing inquiry. Thank you for watching the video. As always, we remind you to post your requests in the comment section. If you enjoyed the video, kindly hit the like button and share it so it reaches more people. Also, subscribe to the feed to avoid missing more content like this. The exploration of our universe, with its vast distances and complex structures, continues to amaze and challenge scientists globally. From early theories about the universe to the latest discoveries made possible by cutting-edge technology, each discovery reshapes our understanding of the universe and expands the boundaries of human knowledge. One of the most critical and enduring questions in cosmology revolves around the origin and evolution of galaxies. Galaxies are like vast cities of stars, gas, dust, and dark matter bound together by gravity. Understanding how galaxies form and evolve is crucial not only for unraveling the mysteries of our universe but also for testing or confirming existing theories. For example, the Big Bang theory, proposed nearly a century ago, suggests that the universe began from a single, immensely dense point and has been expanding ever since. This idea emerged from observations of the universe's expansion and the cosmic microwave background radiation, considered remnants of the early universe's intense energy and light. However, recent discoveries, particularly those made by the James Webb Space Telescope, JWST, have challenged several key ideas central to this theory. The JWST, with its remarkable sensitivity and resolution, has identified galaxies that appear far larger and more developed than expected for their age. One such discovery includes 6 massive galaxies dating back to when the universe was only 200 to 700 million years old, a mere blink in its 13.8 billion-year history. These galaxies, nicknamed universe breakers by the research team, challenge conventional thinking as they are already so large and bright at such an early cosmic age. The discovery of these galaxies raises intriguing questions about the rapid evolution of the early universe and challenges existing models of galaxy formation. According to prevailing theories, galaxies form slowly over billions of years through the merging of smaller systems and the accumulation of gas and stars. The presence of these massive galaxies so early in cosmic history suggests a much more complex and possibly faster process of galaxy formation than previously thought. Moreover, the discovery highlights the critical role of technological advancements in reshaping our understanding of the universe. The JWST's ability to peer deeper into space and capture faint light from distant galaxies has allowed astronomers to uncover previously invisible pieces of the universe's early development. These insights provide valuable clues about the conditions and processes that governed galaxy formation during the universe's earliest ages. The implications of these discoveries extend beyond cosmology. They challenge scientists to revisit and refine existing cosmological models to better account for the observed diversity and complexity of galaxies across vast timescales. They also underscore the dynamic and evolving nature of scientific knowledge, where new discoveries can spark future breakthroughs and open new avenues for research. As scientists continue to examine and interpret data from the JWST and other observatories, the study of galaxy formation remains an exciting and rapidly advancing field. Each new discovery brings us closer to unraveling the mysteries of our origins and helps us understand the fundamental processes that have shaped the universe as we know it today. As we delve deeper into the implications of these discoveries made by the James Webb Space Telescope, JWST, it becomes clear that the landscape of cosmology is undergoing a significant shift. The JWST's ability to capture distant and faint signals from the universe's earliest moments has allowed scientists to observe phenomena that were previously impossible to detect. These observations are reshaping our understanding of the early universe and galaxy formation. It was traditionally believed that the universe's earliest galaxies formed slowly and gradually, with smaller structures merging over billions of years to create the massive galaxies we see today. The conventional wisdom suggested that the first galaxies were relatively small, faint, and scattered across the universe. That massive, well-formed galaxies could exist so soon after the Big Bang was considered highly unlikely. However, the discovery of 6 massive galaxies dating back to just 200 to 700 million years after the Big Bang challenges this long-held view. These galaxies, nicknamed universe breakers, are as large as or even larger than our own Milky Way. This suggests that galaxy formation was far more dynamic and rapid than previously imagined. This discovery forces scientists to reconsider not only the timeline of galaxy formation but also the mechanisms at play during the universe's earliest stages. It suggests that the conditions that allowed such large and developed galaxies to emerge so early may have been vastly different from what we once thought. The fact that these galaxies are producing stars at an extraordinary rate further complicates the situation. It hints that star formation processes in the early universe may have been far more efficient and productive than current models suggest. Additionally, the discovery of these massive galaxies so early in the universe's history raises questions about the role of dark matter and dark energy, which are still not fully understood. If these massive structures could form so quickly, what does that imply about the gravitational forces at work in the early universe? Could dark matter have played a larger role in galaxy formation than we have assumed? How might dark energy have influenced the expansion of the universe, potentially affecting the rate at which these galaxies developed? As scientists continue to analyze data from the JWST and other observatories, the need to develop new models of cosmology becomes increasingly evident. The discovery of these massive early galaxies forces researchers to examine not only the formation of galaxies but also the underlying physics that govern cosmic evolution. The traditional ideas about the Big Bang and the slow, steady development of the universe may need to be revised in light of these findings. Moreover, these discoveries highlight the fundamental importance of technological advancement in scientific discovery. The JWST, with its unparalleled sensitivity and resolution, has opened a new window into the past, allowing us to observe distant galaxies as they appeared billions of years ago. This technological leap forward will undoubtedly lead to further breakthroughs in our understanding of the universe. The discoveries made so far are just the beginning of a new era in space exploration and astronomy. As we look toward the future, it is clear that the study of galaxy formation will continue to be a major focus of research. With each new discovery, we edge closer to answering some of the most fundamental questions about the universe's origins, its evolution, and the forces that continue to shape its destiny.